Hello friends, welcome to my channel. Let's have a look at another easy problem. Problem 108. Convert sorted array to binary search tree. So in this video, we're going to share a method based on recursion. And also we want to make some comments related to the tree data structure or algorithm. So actually in the tree or binary search tree, so the recursion is a very routine technique. So in this problem, we are required to return a height-balanced binary search tree. So here, the given integer array nums is in ascending sorted order. So the second paragraph actually also defines what's a height-balanced binary tree. So a height-balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. So this definition is actually in nature recursive. So here are two examples. So here is one height-balanced tree, and so in example 2, so the problem statement lists two possibilities. So in other words, the height-balanced tree is not unique. So the constraints on this problem are the following. First, the nums array has a length up to 10 to the power 4, and this array is not empty because the length is greater than or equal to 1. So the nums is in sorted strictly increasing order. So this is as stated in the main statement. So with that said, let's look at the method we are going to present. So solving this problem is actually straightforward, but we want to make some remark. So first, the method is recursion. So the idea is the following. Because the goal is to build height-balanced binary search tree. So as the given array is sorted ascendingly, so we try to use the middle element in the array to build root node, and then the subarray to the left to build left subtree, and the subarray to the right to build right subtree recursively. So this way, or this idea, actually can maintain two properties during the process. First is the height-balanced property. So because the left subarray and the right subarray in each recursion call differs by at most 1 node or 1 element. So the binary search property, because we use the left part to build the left subtree and the right subarray to build the right subtree. So because we build this recursively, so the binary search property is automatically maintained. So in other words, as long as these two properties are maintained, so the procedure produces or yields a valid height-balanced binary search tree. So with that said, let's look at some remark. So in general, like the data structures like tree or binary search tree can be defined recursively, or in other words, so they are recursive abstract data structures. Therefore, they provide natural places to use recursion. So problems or tasks such as we check if a binary tree is a binary search tree, or tree traversal, or delete or insertion node in a binary search tree, or find predecessor or successor of a node in binary search tree, and etc. All these tasks can be solved elegantly using recursion. So with that said, let's look at this specific problem. So notice that the nums has length bounded below by 1. In other words, it's never empty. But now let's look at the code. So we're going to build this in a sort of verbose way. But first, we want to treat this case if not nums. So we're going to return null. So or just nothing. So let's so here in the constructor is none. So we are going to let's write a none. So my question may be asked is that, so because nums is never empty, why we do this check? Actually, this check is a stop condition, because if we match single element nums array, then its left subtree and right subtree are actually empty, right? So corresponding to an empty list. So this is the one part. So if the nums is not empty, then we can build the root node. So root equals so the constructor is here, tree node, right? So we're going to write tree node, and then the value will be the nums. So we're going to use the middle one. So it's the length of nums, then divided by 2. So this step finishes the build of the root node. Then we need to build the left subtree and the right subtree and link them together. So we're going to put root left equals our self call. So self sorted. So then we're going to use the left part. So nums. So it's up to this number, but it's not included. So then let's build the right subtree. So another self call using recursion. So then we are going to build the right subtree using the subarray right to this index, right? So we're going to write nums length nums over 2 plus 1 and to the end. So that's the build. So this is the build of left subtree, and this is the build of right subtree, and this two assignment links the node with its left subtree and right subtree. So with that said, we are ready to return the root. So that's the full code for this easy problem. Let's do a special case check. Yeah, it passes a special case. Now let's look at the generic case. Yeah, it passes the generic case, so actually it should be reasonably fast. Anyway, so with that said, I guess that's about it for this specific daily challenge problem. Thank you very much.